is the answer. Or we could realize that we really don't need the memory anymore. We'll just satisfiability problem is empty complete. Whether or not you are following what I'm saying or believe what I'm saying, essentially the assertion that Stephen Cook made in 1970 is that you can take a program and compile it into a common wire one stage to the next. The memory is the circuit, if you wish. That's what this argument is. Just like each state was there so we could reuse the hardware. Okay, you can take a program and compile it into machine code. You could compile it into, so now the signal comes at the top and filters down to the bottom. A gigantic diagram of combinatorial circuitry that computes the program. So here's the key idea of arguing. And this arguing that, where we're going to argue that the circuit size is meant to be a combinatorial circuitry. Yeah?
You can do it in polynomial time?
Okay, so the question then is, well, let me lay a little more groundwork. How deep does this circuit have to be? Yeah?
Maybe however deep you need it to get an answer back at your
Yeah, it depends on how long the depth of this is proportional to the number of cycles that the computer had to go through when it ran the program in the first place. So if your computer took 10 seconds, this is going to have to be 10 times a billion levels deep. All right, so here's the idea. You have a verification algorithm. Remember, every problem from NP has a polynomial time verification algorithm. So what we do is we build a combinatorial circuit that computes that verification algorithm. The inputs to the verification algorithm come in at the top, and out the bottom is a single bit that says yes or no. The verification algorithm verified or did not verify. So we build that combinatorial circuit. At the top, we put an instance onto the appropriate memory inputs. Okay, so what are the inputs to a verification algorithm? What does a verification algorithm take as inputs? Yeah?
The proposed solution.
The proposed solution, and also a description of the proposed instance. So what we do is we have at the top where the inputs to the circuit are. Think of them as a bunch of wires. Some of the wires correspond to the bits of the problem instance, and we set them to describe the problem instance. Some of the wires that come at the top contain the proposed solution. So if we set those as well, and then let the circuit settle down, there'd be a bit coming out the bottom that said whether or not that proposed solution was correct. But what we're going to do is leave the bits corresponding to the proposed solution unbound. Okay? So now we have a combinatorial circuit with input at the top corresponding to the problem instance and an output at the bottom corresponding to the result of the algorithm. And the circuit satisfiability problem is just given a circuit, is there a way to set the inputs so that a true will come out the bottom? Okay? So if we had an implementation of the circuit satisfiability problem, we would just feed it this, give it this circuit diagram and ask, is there a way to make true come out the bottom? And that corresponds to finding a solution to the problem instance, similarly to how we're doing with method satisfiability. Now, how deep will this circuit have to be in terms of the size of the input at the top? Yeah?
At least as big as the input?
Well, it had to do with the time that a computer would take to run the input. Yeah?
Based on the size of the problem instance?
Well, it would depend on the size of the problem instance and the size of the proposed solution. Yeah?
It would scale polynomially?
It would scale polynomially. Because the amount of time, the verification algorithm is polynomial time. That means the time it takes the computer to execute it, the number of steps it takes the computer is polynomial in the size of the input. That means the depth of our circuit is polynomial in the size of the input. Okay? Yeah?
Can you give us like an example of a circuit that...
Well, I'm drawing you a picture. I'm not going to give you a real circuit. Again.
Put that up. And stop working.
Yeah, it's a different pen. It was working before class. Okay, so we have our verification algorithm. And we compile it into a gigantic combinatorial circuit. It has the property that we feed it at the top a problem instance and a proposed solution. And out the bottom comes a single bit, which tells you, is solution correct? The depth of this circuit is O of n to the d, where d is some constant, and n is this is n. Okay, because we know the verification algorithm is polynomial time. The circuit satisfiability problem is to take a circuit like this and find inputs at the top that will force a true to come out the bottom. We're going to hardwire these wires to have a particular problem on them. So then, if we apply the circuit satisfiability problem to this, the algorithm to this, we would find we're basically finding a proposed solution which will force a 1 to come out the bottom. So we're solving the problem. So given that setup, how do we argue that circuit satisfiability is NP complete? How do we do that? What's the argument? Yeah.
So you have to make two arguments, right? The first one is it's NP, and that's obviously NP. Yeah.
Okay, so first we have to argue that circuit satisfiability is a member of NP. So someone else tell me how we do that. Yeah?
Should we take an existing member of NP and then reduce it?
No, that's a different issue. What's it mean to be a member of NP? Yeah.
It can be verified in polynomial time.
That it can be verified in polynomial time. So in other words, if someone gives you a circuit and claims if I set the inputs to these values, a true will come out the bottom, you have to be able to verify that in polynomial time. Okay, so do you think the circuit satisfiability problem is a member of NP? Yeah, it's easy to verify. If someone gives you ways to set the inputs, you just run the circuit. You know, just simulate the circuit and see what comes out the bottom. Yeah.
And then the second step, you have to show that all of NP maps to that.
Okay. We need to show that every problem from NP reduces in polynomial time to an instance of the circuit satisfiability problem.
So this would be like synthesis and parallel.
So how do we argue that there is a reduction? Given a problem from NP, what's the reduction? Yeah.
Start with 3-stat and reduce it to circuit.
No, we don't start with, no. We don't know any other problem is NP complete.
Oh, okay.
This is how we prove 3-stat is NP complete.
Okay.
So where do we start? How do we, given a problem, how do you take any old problem from NP, how do you show that it reduces to this in polynomial time, to an instance of circuit satisfiability? Yeah.
So for any problem, if you have an instance of it, then you can plug in the instance into circuit satisfiability in polynomial time, because that's just, plugging it into circuit satisfiability is just pretty much linear with the problem size. And then because building the combinatorial circuit is also polynomial time, then that specific instance of NP problem will reduce to circuit satisfiability in polynomial time.
Okay. So the bottom line is every problem from NP has a polynomial time verification algorithm. So suppose you want to solve some problem from NP. Call it problem X. We take its verification algorithm and compile it into a circuit. Now, we can compile it in polynomial time because we know that we have a polynomial time algorithm and it'll map into a polynomial size circuit. So you take any old problem out there from NP, you take its verification algorithm, you compile it into this combinatorial circuit. You take the input, you take the problem description, you hardwire it up there as the problem, you leave the problem, the proposed solution wires unbound to trues and falses. And then you run the combinatorial, you run this algorithm, circuit satisfiability, and find out, is there a way to set the proposed solution bits to get a 1 out the bottom? And if there are, you will have solved the problem X. If there aren't, you'll know problem X has, the original problem X having a solution. It'll work for any problem in NP because they all have verification algorithms. That's the key. Yeah?
So what does that circuit look like?
What's it look like?
Yeah, that solves everything.
It doesn't solve everything. It solves, you know, this is different for every problem you come up with. Right? This circuit here, it just depends on the verification algorithm. Right? Just like every verification algorithm will compile to a different set of machine code, every verification algorithm will compile to a different set of ands and ors and nots. It's this algorithm that can solve any circuit. And what I've shown you is that you can sort of trick this algorithm into solving any problem you want by taking that problem's verification algorithm and compiling it to a circuit. Then you can apply this magic algorithm to it. Yeah?
I'm so confused on how do you choose proposed solutions?
You don't have to choose a proposed solution.
How do you set the wires for that?
You don't. So these wires here, you're going to set them, 1, 0, 1, 1, 1, whatever it takes to describe the, the problem. These over here, you do not. You leave them unbound. The circuit satisfiability algorithm takes this circuit and says, okay, there's a bunch of inputs here. Is there a way to set those inputs that makes a 1 come out the bottom? And that's what the circuit satisfiability algorithm does. It finds a way to set these to trues and falses such that a 1 comes out the bottom, thereby finding the solution. Yeah?
So then the circuit satisfiability is not described here. This is just the combination circuit is
This is a circuit that corresponds to a verification algorithm.
So then that's just a whole other circuit somewhere else.
This is an algorithm that's able to analyze circuits,
Okay.
find a way to set the inputs, the unbound inputs, so that a 1 comes out the bottom. And the way that the inputs were set is then the solution to the problem this was compiled from. Yeah?
So is it tried many times with many different...
Who knows how it works?
Huh?
Who knows how this algorithm works? Doesn't matter how it works. What we've argued is, if you can do this, if you can solve this problem efficiently, you can solve any problem from NP efficiently. It's not our job to say how to design this algorithm. We don't have to find it. We're just showing that if you can solve this problem, you can solve every problem from NP.
So this is like
Without solving this problem, how do you know that you can solve it in polynomial time?
We don't have to show that either. We just have to show that you can produce this thing here in polynomial time. Given a problem instance, you just have to show that you can produce this circuit in polynomial time. Yep.
If you could solve circuit satisfiability in polynomial time, wouldn't that mean P equals NP?
Sure.
Okay.
Yeah.
I'm sorry, this might be backtracking a little bit, but are we assuming, just assuming that circuit satisfiability is NP complete then?
No, we're proving it's NP.
Proving, okay. That's the point of this.
The whole point is to prove circuit satisfiability is NP complete. Yeah.
Because doing that, we can then reduce every other problem to...
Well, to prove that circuit satisfiability is NP complete, you have to prove that every problem reduces to it. The reason every problem reduces to it, every problem in NP, is that every such problem has a verification algorithm, meaning it can be compiled in a combinatorial circuit of limited depth. It can be compiled in a combinatorial circuit in polynomial time because the running time of the algorithm is polynomial time. Once you have compiled it into circuitry, you could take a satisfiability algorithm and run it and figure out how to set the proposed solution bits such that a 1 comes out the bottom, thereby solving the problem. Yeah.
So how do we know again that circuit satisfiability can be verified in polynomial time?
Okay. Someone gives you a combinatorial circuit and says, if you set those bits to 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 1, a 1 will come out the bottom. So how would you verify that assertion? You just simulate the circuit. So it's easy to verify. We don't have to come up with a way of solving it. We're just showing that if you could solve this efficiently, solve that problem efficiently, you could solve anything. Yeah?
Where does this algorithm fit onto your block diagram? Did you leave it like intentionally isolated over there by itself? Or is it
Yeah.
it's happening at the bottom kind of? Or like
No, this algorithm analyzes circuits like that. This thing here is the input to this algorithm. Circuit satisfiability takes the description of a circuit as input and figures out how to set the inputs to the circuit such that a 1 will come out the bottom. Yeah?
So if we don't have to show the circuit satisfiability, who's to say it doesn't run polynomial time? Where is that assertion? Couldn't it? If it's a black box in the situation.
Yeah, we don't. Right. We don't have to say anything about the algorithm for this.
Okay.
There may be a polynomial time algorithm, or there may not. That's unimportant to the proof. To do the proof, we just have to show we can take any problem from NP and reduce it to this problem in polynomial time. Okay? This is completely analogous to what we did with method satisfiability. There, instead of taking verification algorithms and turning them into circuits, we were taking them and turning them into programs. That's exactly the same idea. Okay? So that means that this problem, circuit satisfiability, is NP complete. Now, you could take any combinatorial circuitry here and turn it, there's a bunch of inputs up here. We'll call the inputs x0, x1, and so forth. Do you believe we could take this circuit and describe it with a Boolean expression? Right? We could, it might be x0 and x1 bar, or blah, blah, blah. It'd be this massively long description of this. So that means that the problem, that argues that if this problem is NP complete, then the problem of taking a big old Boolean expression and deciding how to make it true is also NP complete. Problems are equivalent. And then it's possible to prove that you can take any expression in Boolean logic and turn it into a three-sat expression. Right, we won't do that proof. It just turns out that you can take any arbitrarily complicated Boolean expression and turn it into three-sat form. So three-sat's NP complete. And now we're off to the races. We've got an NP complete problem, several NP complete problems. Now we can start using them to prove other things are NP complete. Okay? Yeah?
So when you first proved that circuit satisfiability is NP complete, you also did subsequent reductions, and you're like, right? Did you publish multiple papers? Or?
I'm not sure exactly the timeline, but he published this problem about NP completeness. And then there were a couple other researchers that became famous by proving other problems are NP complete. I'm not sure exactly how many Cook proved. Okay? But if, I understand this is probably, this is opaque to a lot of you. So I just got two pieces of advice. If you don't understand the circuit argument, look at the method satisfiability argument. It's probably more accessible because it deals with programs instead of circuits. You're more used to thinking about programs. The other thing is, I guess the key thought to keep in mind is the only thing that all problems in NP have in common is that polynomial time verification algorithm. So both the method satisfiability proof of NP completeness and the circuit satisfiability proof of NP completeness depends on that fact. It depends that they all have verification algorithms. You can take the verification algorithms and turn them into inputs for either circuit satisfiability or method satisfiability, and thereby solve any problem from NP with a single algorithm. Yeah?
The one thing that's bugging me is I'm just not clearly seeing why the circuit satisfiability time is just irrelevant for the proof. How come we don't have to worry about it at all? We just have to set it up this way and say, good, then it's NP complete.
Because what's the definition of a reduction? What's it mean for X? What if we say X reduces to Y? In polynomial time. What does that mean? What does it mean to have a reduction from X to Y? A polynomial time reduction from X to Y. Yeah?
If you have like a function that solves y, you can just call it in x and they'll solve.
Well, that's a consequence of the reduction. But to reduce X to Y, you just have to show how to take any input intended for X and turn it into input intended for Y, such that then if you solved it, you would have a solution to the original X. If you solved Y, you'd have X. The reduction doesn't. The reduction says that the conversion of the input intended for X has to be converted into input intended for Y. That conversion has to happen in polynomial time, which is to say, in this case, this circuit, you have to be able to produce the circuit in polynomial time. And after you have solved the instance of Y, you have to be able to take the output produced by the algorithm for Y and turn it back into output for X. That has to happen in polynomial time. But the solving Y itself, the reduction doesn't say anything about that. But as a consequence of all this, if you could solve this in polynomial time, you could solve any problem from NP in polynomial time. Yeah?
Just to be clear, like the reduction also includes the steps that we transferred the output of y back to the output
Yeah.
of x.
You remember the diagram I gave you with, the stages. There was the box. In here's an algorithm for Y. There's F, and there's H. And this big box is intended to be an algorithm for X. So you take input intended for X, you convert it into input intended for Y. Out comes a solution for an instance of Y. H turns it into an output for X. So externally, input for X goes in the box, output for X comes out. Internally, F and H are, F modifies the input, feeds it to Y, takes the output of Y, modifies it, produces the output. H and F have to be polynomial time algorithms for this to be a polynomial time reduction. You don't even have to know an algorithm for Y to say this is a polynomial time reduction to Y. So in our case, X is any old problem with a verification algorithm. Y, an instance of Y will be this circuit. Y itself is the circuit satisfiability problem. Yeah. So, this can take a while to sink in. And I do think that the method satisfiability problem is more accessible than this. Yeah?
Is there anywhere you recommend looking at
I'm sure you can find lots of resources on the web, but I think if you just trace, if you go back to my slides and go through method satisfiability, forget about circuit satisfiability. It's the same idea, but I think it's more accessible. That's what I would look at. Okay, so this repeats what I was just saying. So, some problems don't belong to NP. There are lots of problems that don't belong to NP. In fact, there are some that are known to be so hard that it's impossible to solve them with a computer. Okay? You talk about problems like that in the CS4100. But I'll give you one example here. This is an impossibly hard problem. You can prove that there is no way to write a program to solve equations of that form. So the idea is, these are called Diophantine equations. It's just polynomials and multiple variables, where all the variables and all the coefficients are integers. Okay? So the idea would be you've got to find an x and y and a z, which are integers, that you can plug in there such that the equation is solved, or report the equation can't be solved. Now, at first look, you wouldn't think that's an impossible problem to solve. Yeah?
Well, I mean, it seems like you could verify this problem in polynomial time.
Okay, could you? Okay, so that's a good question. Why is it not a member of NP? Why can you not verify polynomial time? Yeah?
The answer could be irrational, so the input would have to be pretty big.
Well, no, the answer can't be irrational. The answers have to be integers. Yeah?
Given that x, y, z, you can...
Sure, given an x, y, and z, you can plug in and see. So why is this not a member of NP? Yeah?
Because you can't reduce it down, or, wait, no, that would be,
Right. What's the catch here? I mean, surely if someone gave you an x, y, and a z, you could plug it in and see. Yeah?
Is it because the solution isn't unique to the instance?
It doesn't have to be a unique solution. You just have to find a solution. Okay? Yeah?
Is it because the verification is faster than polynomial time?
No, not that it's faster. Yeah.
Is exponentiation for large numbers not polynomial time?
Well,
Or not exponentiation, but the actual, like,
you mean yeah, all the exponents are going to be constants, and so you know the exponentiation of the time is proportional to the size of the number. Yeah.
it's possible that the only solutions are so big you can't find them.
Well, no, it's not that they're so big you can't find them. The solutions may be gigantic integers. The verification algorithm has to run in polynomial time, where the size of the problem is, the number of bits it takes to describe the equation. So you can have really small equations with gigantic solutions, where the numbers are, say, trillions and trillions of bits. Yes, you can verify, but the verification takes longer than polynomial time, because the numbers are so much larger than the equation. Yeah?
But isn't n the number of bits?
Yeah, n's a number of bits.
So then...
So it would take, I don't know how many bits it would take to describe that equation. Not many. Right? I mean, we could just describe it in ASCII. Let's say 8 bits per symbol. So take the number of symbols times 8. You could certainly describe the equation in that many bits. Okay? But the solution, proposed solution, might be dwarf infinite. Could be exponential infinite. You can't, the solution could be arbitrarily large. And so large that you can't, yes, you can verify it, but the time it takes is all out of proportion to the size of the equation. Yeah?
What happens if there's no solution?
Well, if there's no solution, that's a possibility, but you don't have to have a verification argument for no solution. Yeah?
What do you mean by the size of the equation?
The number of bits it takes to write down the equation. Okay, I can write that equation down in a few inches of slide space. But what if the values of x, y, and z that are the solutions, won't even fit on the slide? Consist of trillions of digits, which they could. You can write a simple equation whose solution is, where the solutions, the x, y, and z values, are trillions of bits long. Yeah?
I just don't understand, because if they are trillions of bits long, that would be the size of your input.
No.
So that...
No, this is the input. The verification algorithm has to be polynomial in the size of the problem instance, not in the size of the proposed solution. So you have to be able to verify a solution in polynomial time in the size, where n is the size of the input to the problem in the first place. Yeah?
Why couldn't you just design a computer with like a trillion bit integer registries and then just...
Fine, then I'll give you the trillion squared. Numbers that are even bigger than that.
Numbers are in binary, right? Not in like unary, where we can...
Yeah, I'm not talking about unary. So anyway, That's not typically, problems from NP. The solutions are, the same order of complexity as the problems in the first place. Okay, so that's why it's not a member of NP. Why can't it be solved at all? I can think of an algorithm to solve it. How would you do it? What if it was a caddis problem? How would you try it? Yeah?
Generate permutations of integers and just...
Right, you try all possible triples of integers, right? Write up one loop that iterates x through all integers. Maybe it goes 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4. Systematically tries all values for x. Then have a nested loop that tries all values for y, and a nested loop that tries all values for z. And it runs until it, for each combination, it evaluates the equation, sees if it holds. If it does, it's found the solution. Just need a big integer package and enough time. So why am I saying it's impossible? Yeah.
Because it's possible there's no solution.
It's possible there's no solution, and we've got to report that in finite time. And what I just suggested to you, if there is no solution, you'll never find that out. The program will just run forever. So it's been proven that there is no way, in general, to solve this problem. Yes, if there is a solution, you can write an algorithm that finds it. The problem is an algorithm that will discover that there is no solution in all cases. Yeah?
So the algorithm you're describing has nested for loops that will come to an end, so
No, they won't come to an end.
why won't they come to an end?
Because we're iterating over all integers, an infinite number of integers.
Why is it an infinite number of integers?
There are an infinite number of integers. I'm not talking about machine ints. I'm talking about mathematical integers. We don't know how large x, y, and z are going to have to be to have a solution. Right? So we just have to keep going. Now what I've said isn't a proof that this is unsolvable, but I'm giving you an idea why it's unsolvable. Okay? And sort of the more famous impossible problem is the halting problem. And that problem is, what that problem does is it looks at a program and its inputs and says whether or not it will halt on those inputs.
So it's like a debugger.
Okay? So how would you solve, if someone said, give me a program that will solve the halting problem, right? It would have to take, imagine it's a Java program. It takes another Java program as input and says whether or not it'll halt when it's run. How would you implement it? Yeah?
I just want to clarify, is this like testing all possible inputs to the program?
No.
Is it just one set of inputs?
No, one set said, here's the program, here are its inputs. Will this program halt when it's run, yes or no? Yeah?
So couldn't you, are you asking like how you would implement it?
How would you implement an algorithm? How would you implement a program that solved the halting problem? Yeah?
The only way I can see is just run the
Right. You could take the you're given a program and some inputs, and you ask, will this halt when it's run? So you run it. And if it halts, you report, yes, it halts when it's run. But what's the problem? Yeah?
They just go infinite.
Right. How do you say that it doesn't halt? You'll never know for sure if it's not going to halt. It's just going to, so you'll never give an answer because you just run it and you'll never see it not halt. So now you have to try more sophisticated techniques. Maybe instead of, your debugger, your compiler will tell you sometimes you got an infinite loop. If you write while true and there's no way out, you might find out there's an infinite loop. There are lots of cases where you could just stare at the code and decide, you can do that. You can say, yeah, this is an infinite loop, this program will never halt, this is infinite recursion, it will never halt. But it's been proven, and actually it's not hard to do the proof for this problem, that can't be done. In general, you can't tell whether or not a program is going to run forever. Some cases you can, but in general you can't. So this can't be done. Yeah?
So this program takes program as input. So couldn't you put itself as an input?
Yeah. So the halting problem is the classic unsolvable problem. Now, suppose we could solve a halting problem. Would that help us with this thing? So what we could do if we had the halting problem solved is what we would do is take that input instance, we would write a program that tries all possibilities to solve that equation, and then instead of running the program, we would just ask, does this program halt? If the answer is no, that program does not halt, we would just report, this equation has no solution. If we're told the program does halt, then we run it, and we'll eventually get the solution. So it would be a great utility if we could solve the halting problem. Yeah?
So is it the case with all unsolved problems that one part of the output is just impossible to reach, it would take that time to figure out, like for the first one, like obviously we would need to, it would be hard to find out if there was no solution, and then the next one, we would need to, it would be hard to find out if there was a solution.
Yeah, in both of these cases, the problem here is what happens, the obvious solution fails because what happens when there is no solution? The obvious program is going to run forever. Same thing down here. The obvious approach is just to try the program to see what happens, but if it runs forever, you're stuck.
So is that a general thing over all unsolvable problems that they're?
No, that's
just like,
yeah, sort of, but that's not how you prove problems are unsolvable. That's just a way that you gain some intuition about them. Yeah.
Are unsolvable problems like NP complete where you solve one, solve the rest, or is it just a constant?
Yeah, the same thing happens where you have this class of problems. These problems are what are called recursively enumerable problems, meaning you can this one here, meaning if there is a solution, you'll eventually find it. If there's not a solution, you may run forever. And and then all these problems, if you could solve the halting problem, then you would have an algorithm for all of them. So there is sort of this parallelism between NP completeness and between non-recursive programs. Yeah?
So I'm just curious, this problem that is unsolvable, where did we first see it, or where was it created, or?
Well, the problem of solving Diophantine equations is just a classic problem in mathematics. Won't define integer solutions to equations.
So one day someone was like, I'm going to come up with something really hard that no one can ever solve.
Well, no. Probably. This may have, in fact, have been one of the, there was a set of challenges, right around 1900, mathematical challenges to find, I think one of them was to find an algorithm to solve Diophantine equations. And eventually, rather than finding an algorithm, it was proven that there is no algorithm. Now, like I've said before, this is sort of the story of 20th century mathematics, where a lot of the most famous results in 20th century mathematics are proofs that things can't be done. Limits to what can be proved, limits to what can be computed. That's basically what Turing did. So Alan Turing, among other things, proved that there are problems that can't be described with programs, can't be solved with programs. And the interesting thing about Turing is that he did this work in the 30s. So he proved fundamental results on the limits of computing before there were computers. Yeah.
Right. Can we solve this using like vector calculus?
You could solve them for real numbers. You could come up with floating point approximations of the solutions. But to solve exact solutions over the integers, no, there's no algorithm. It's known that there is no algorithm to do it.
Are you going to give us more problems? Are you going to give us more problems that can be solved?
No, that's I'm going to stop there. Yeah?
Sorry, one of these could be solved. Does that trickle down into the NP complete problem?
Well, no. I mean, you can't. I mean, you can't solve these problems. Yeah.
What about any modern day quantum code solutions or anything quantum going on in regards to these problems?
I have never read any relation between this and quantum computers either, but that doesn't mean much. Okay? So in addition, these are problems that are just, can't be done. There are also problems that are not members of NP, but which can be solved, but which have been proven to require exponential time or worse. So there are all kinds of classes of problems. NP complete, NP and NP complete and P are sets of problems, but there are theorists have named lots of sets of problems that have different characteristics. For example, I told you that linear programming, that problem is actually P complete. Right? Meaning any problem that you can solve in polynomial time, you can solve with linear programming in polynomial time. Okay, so we've defined NP completeness. Now we're faced with the fact that there are lots of NP-complete problems, and we need to write algorithms for them. FedEx isn't going to stop delivering packages because they can't determine the absolute optimal route for their trucks to take quickly, because that would require solving the traveling salesman problem. So they got to do the best they can. How many of you have written a program to solve an NP-complete problem? Okay? All of you have. Spider-Man's workout is NP complete. Yeah?
What if we didn't pass the second test case?
Well, then you haven't written the correct program. You've tried to write a
But
yeah.
isn't Spider-Man's workout just a constant time problem because you bounded the inputs?
well, the inputs are bounded, yeah, but if you don't say that don't limit the bounds at 40 steps, the general problem is NP complete.
But the height of the building is only 10,000.
Well, again, they're arbitrary. Why are these arbitrary bounds put in? Why did they only allow 40 steps? Why did they allow...
You can force it to polynomial.
Because then it can be solved quickly. They made the limited height enough so that you can solve it quickly. But the general problem is NP complete. Let's take a break and we'll talk about that.
Yeah.
Okay, let's get started again. Okay, let's think about that. Spider-Man's workout. You strip away Spider-Man, you strip away the buildings, you just look at the array of numbers that you've got. What's the, what are you being asked about the numbers, roughly? Yeah?
If you could find a sequence of numbers that sum to 0 without going negative.
Okay. Yeah?
You can find two sequences of those numbers that are equal to each other.
Okay.
Using all the numbers
Right.
in the set.
That's a productive way to think about it. Let's forget about the negative constraint, which just makes the problem harder. You can't go below 0. Fundamentally, what you're doing is you're given a set of numbers and you're trying to split them into two subsets such that this set adds up to the same thing as this set. So think of one set as being the places where the times you go up. The other set are the times you go down. So the ups have to add up to the downs. What problem does that sound like? Subset sum. So it's sort of the subset sum problem, slightly modified or somewhat modified. But the way you would prove it's NP complete, you could start with subset sum and work at it and prove that that problem is NP complete. Yeah.
So why wasn't it a good idea to start with subset sum and reduce it to Spider-Man's workout?
Well, we don't have a fast algorithm for subset sum. It's NP complete, so probably the best algorithm for that's exponential.
Didn't you show that subset sum reduces to box bin packing? So we could
Well,
bin packing.
Yeah, bin packing is another problem I talk about on the assignment. So I don't intend to go in details to prove it's NP complete. But in fact, I didn't even realize it until this weekend, and I was just thinking about it, and I realized, yeah, that problem's NP complete. Nevertheless, you without knowing that, you wrote a program to do it. Now that means that you can solve certain size problems, but if as the problem becomes bigger, your solution is going to fare less and less well. Okay? As far as we know, the best solution to the Spider-Man's workout is going to be exponential time as well. Yeah?
The art gallery one incomplete?
I don't believe so, no.
That's polynomial. You can construct the, it's NQ.
Yeah, I don't believe it's NP complete. What makes Spider-Man's workout bad is that you can have again, eliminate the arbitrary bounds. You can have small numbers that describe the ups and the downs, but then the maximum height to which you might reach can be much larger. So you can have, say, 20-bit numbers describing the ups and downs, but now you need a million, your dimension in the height direction is a million now. So it's that problem we see again where small inputs end up with large solution space. My larger point is people try to deal with NP-complete problems the best they can all the time. And there are various approaches. Some problems have special cases that can be solved efficiently. Some NP-complete problems have special cases. So you might just concentrate on special cases. There are approximation algorithms for some NP-complete problems. There'd be a problem that you can't solve, in general, you can't solve it exactly and quickly, but you can find an algorithm that gives an approximate solution quickly. And that's good enough if you're delivering packages, for example. You may not find the absolute best route that saves the most gas, but you can come close, let's say. And then there are two techniques for dealing with search problems and optimization problems. Search problems, you use backtracking, intelligent backtracking. Optimization problems, exhaustive search.
Slideshow.
Now, what I want to do, I could sort of step through it in a particular order, but I'm going to skip ahead. We'll come back and talk about backtracking. I want to talk about optimization problems because you've got to start working on your caddis problem or something. Okay, so branch and bound. In fact, I'm going to show you recursive branch and bound. All right, branch and bound is a technique that you should use, I recommend you use for doing this TSP problem, this final caddis problem. So let's think of what is the brute fortiest, anyway, the most brute force approach you can think to solving the traveling salesman problem. So let me just remind you what it is. You've got a graph. In the case of the TSP problem on caddis, the graph is known to be complete, meaning there's an edge between every pair of vertices, okay, which makes it bad for the traveling salesman problem because there's so many possible. It's no problem at all. No matter where you go, you can find a circuit. And finding a Hamiltonian cycle is no problem. You do it with your eyes closed because there are no missing edges. Put the vertices in any order, and and that'll form a cycle. The problem is, since there's so many cycles, what's the smallest? What's the smallest weight cycle? That's the traveling salesman problem. So, what's the brute force approach? Yeah.
Enumerate all the permutations and find the minimum.
Right. You find all the permutations. So basically, you start somewhere. Start at vertex A, and you try going to B. So you go from A to B. You make a recursive call to close the loop from B back to A. If that, and you find out the best you can do with that. And then when the recursion returns, now you instead of going from A to B, you go from A to C. And then you try A to D. So you're constantly backing up and trying a new direction. And you do that recursively. So the organization is going to look like this, roughly. So you're trying to minimize the solution to some problem. So you start with the initial problem, P0. P0 is solve the traveling salesman problem for this graph. In the case of TSP. We'll ignore the best so far right now. We call optimize of P0, and if it didn't find a solution, we report failure. Otherwise, we report the answer. So think of best so far as being the variable that's going to contain the answer at the end. So initially, best so far is infinite. We systematically, in this method here, we systematically try all possible routes, all possible paths, all possible cycles. As we close each cycle, we figure out what its total weight was. If it's better than what we've seen so far, we remember it. When we're done, we found the best solution. And so the programming comes down to actually the very simple problem of enumerating all the edges. Very simple recursive function. Okay, now let's think about what it takes to optimize. You've got a problem to solve. Initially it's P0. So you've got a problem to solve. You look at the problem and you say, is this a complete solution? Well, initially P0 is not solved. What I mean by a complete solution is if you reduce the problem to nothing, meaning you solve the problem, then you update best so far. You see if your subproblem is a solution, you see if it's better than the last best solution you have, if so updated. Otherwise, you've got to expand each subproblem. You expand P into some subproblems and you explore each one in turn. So what that would mean is, let's say your initial problem is to start at A and find a path back to A. This is a vertex. The subproblems would be go from A to B and then find a path back to A. Go from A to C and find a path back to A. Go from A to D and find a path back to A. So those would be all the subproblems. So you recursively solve them. So your program consists of, in terms of traveling salesman, of a loop that's trying all the paths out of your current vertex by making a recursive call. So a recursive call inside of a loop. This is what makes it possible to do it efficiently. And I'm going to show you what I mean. So here's a graph, traveling salesman problem. So you write a program that, say, just picks a starting vertex, and that's going to be A, and tries to find the best cycle that starts at A and ends at A, and this is every vertex once. So in this graph, the unnumbered edges all have weight 1. So we could write, like I said, you could easily write a recursive program that exhaustively tries all ways of getting through this path and getting through this graph in a cycle and finds the best one. Let's see if we can do it a little bit better. So this technique is called branch and bound. Suppose that we have already got A, B, and C. We've grown our path. So A, B, and C, we're trying to now close the loop. I want to put a lower bound on how well we can possibly do before I try to solve the problem. Now, why would that be useful? Why would it be useful to come up with a lower bound? We know we're going to go from A to B to C. Yeah?
Once you hit that as your base case, you can stop, like,
Well,
trying to find something better.
we don't. It's not that we hit the base case.
Or,
Suppose I told you that, okay, if we start with A, B, and C, you're not going to do better than 10 or 14 or something. Yeah?
Doesn't that let you look at a different path that's at least 2 edges deep? That perhaps is a...
Well, but what specifically do you do with the information? Yeah?
You fast forward to 10 or 14. You fast forward to your lower bound, so you don't have to compute everything from 0 to your lower.
Yeah. Sort of, yeah.
If you ever pass 10 or 14, you can just quit looking, right, for that specific.
Okay, suppose that you've already found, remember the way this works is, you are trying, it's going to find some path back to the start and see what it's worth. Then it's going to back up and try a different way. It'll try all the ways out of the last vertex. And it will back up to the one before that and try all the ways out of that. Systematically, it'll find every possible path. Each time it closes the path, it'll see, is that better than the last best solution we found? And if so, it'll update. So suppose that you have already found a path of length 10. And now you back up and you're trying A, B, C. And someone says, you know, if you go forward with this, you're not going to do better than 14. What can you do with that information right then and there? Just say, okay, I won't try. So rather than try and fail to do better than 10, if you know that you're not going to do better than 14, you back up from, you try a different way out of B, because the way you're trying isn't going to lead to success. The question comes down to, how do you put that bound on? Yeah?
Add up the weight of the edges to start.
Well, you certainly use the weights of the edges. So for example, let's go from A to B to C. Okay, we've already spent 3 units getting from A to B to C. How many more edges do we have to add to close this thing? Actually 6, right? We got to go, let's say we went from D to E to F to G to H and back to A. That would be 6 edges. So we know that we've got to add 6 edges. We know that each of those edges has a weight at least 1. So quick bound would say, okay, 3 for the edges we've used, 6, a minimum of 6 for the ones yet to be used. We can put a bound of 9 just like that. Okay? So branch and bound is you're constantly putting a lower bound on how well you can do if you go forward. If that bound ever becomes higher than the best solution you've seen so far, you bag it right then. You don't have to do a bunch of backtracking. The earlier you can prune, the better. Okay? And so your TSP algorithms are just going to come down to implement branch and bound, or actually implement exhaustive search, and then improve it by, each time you get to a new vertex, estimate how much it's going to cost to finish, and if it's going to cost too much, don't explore any further. Back up, try a different way. Yeah?
Does it mean for all of our caddis problems, every node is going to touch every node?
Yep, every node is going to touch every other node. So there's going to be plenty of choices of ways to go. Yeah?
Sorry, so I'm kind of confused on the difference between the lower bound and the best so far.
Best so far is a solution you have actually found. And it's an honest-to-God solution. The lower bound is just, it says if if the lower bound is 14, we're just saying that if you continue, you're not going to find a solution that's better than 14. You may not even get one that's as good as 14. So if the lower bound is higher than the best so far, it's pointless to continue. You need to back up and try a different way. Yeah.
So with taking an approach like this on our last caddis problem, would that be faster than the dynamic approach?
No. No. In the last caddis problem, yeah, exhaustive, it would have taken exponential time. Okay. So we have this. It's going to come down to how well you can put a bound on things. It's also, but it's not enough to have an accurate bound. You have to be able to compute the bound quickly. If you take a lot of time to get a really accurate bound, you haven't saved much time in it. You may have wasted time because you're spending all your time estimating and not enough time searching. So you need quick and effective ways of doing this. Now what I'm going to show you is sort of a classical technique to do it, but I don't think it'll work. In fact, I know it won't work for you very well in practice. We've got some improvements. And this is the bound. We take what we spent so far, which is 3, that ABC distance. We take, we compute the minimum spanning tree that hooks all the unvisited vertices together. Okay? Why minimum spanning tree? Why do we compute the minimum spanning tree of D, E, F, G, H? Why do that? Anthony?
You're going to have to visit all of those nodes.
Right. There's going to be, if we solve the problem, there's going to be a path that connects D, E, F, G, and H together. That'll be a piece of the solution. It'll visit them in some order. Among other things, that path is a spanning tree. It connects all the vertices together. And it can't have a weight any smaller than the minimum spanning tree that hooks all these vertices together. So we take the known cost, ABC. We take the minimum spanning tree that hooks those things together, D, E, F, G, and H. What else do we need to add in? Yeah?
The lightest edge from C to the minimum spanning tree, and the lightest edge from the minimum spanning tree to A.
Right. We gotta hook the path ABC to the minimum spanning tree. So we take the lightest edge out of A out to one of those, and the lightest edge from C out to one of those. Add those together, that's our lower bound. Now, here's the problem. Yes, we know an efficient way to compute minimum spanning trees, but it's too expensive to do every time you push out to a new vertex. And so to make this really fly, what you have to use are what are called incremental algorithms. An algorithm that takes a minimum spanning tree that you've previously computed and modifies it. So as we explore out, let's say we have a minimum spanning tree for H, G, F, E, and D, and then we take D, we decide to go from C to D. So now we need to shrink the minimum spanning tree. So you need to have an efficient way to take the larger minimum spanning tree and shrink it down. So I don't recommend you use this technique. This is to illustrate branch and bound. You need to find cheaper ways of doing the bounding, and we'll talk about some possibilities. Okay, so let's see how it would work. We're going to take the distance of A, B, C, the lightest edge from A to one of the out vertices, the lightest edge from C, and the way the minimum spanning tree would be. So let's start at A, and first thing we'll do is I figured out that right off the bat, there's a bound of 8. So where'd that bound come from? Yeah?
To create a cycle, you must have at least 8 edges, and the minimum weight of an edge is 1.
Well, but I'm using the minimum spanning tree approach.
Oh,
Okay? So, right, so there's no, A is by itself, so that's 0. We take the lightest edge from A out into the forest, and that's 1. And the lightest edge, another lightest edge out from A into the forest, that's another 1. So that's 2 so far. Then we compute the minimum spanning tree of B, C, D, E, F, G, and H. And it turns out that's 6. Can you see how to hook them all together with called 6? There's 7 vertices. So like we hook B to E, E to F. We go B, C, D, G, and then B to E, B to F. So that gives us
E to F.
E to F, yeah. That gives us 8. That gives us 6 for the tree, 2 for the edges connecting A to the tree. Okay? So we're not going to do better than 8. So we go try explore to B. Okay? What's the bound now? What are the components of the bound? Yeah?
So wouldn't it be the weight of the vertex connecting them?
Okay.
And then whatever's left would be 1 more?
All right, so 2 plus 1 for getting from A out to the white vertices, and 1 from getting B out to the vertices. So that's 4. And then the weight of the tree for those 6 vertices.
5.
Okay? So how can you cook together all those the cheapest way possible?
How you hooked A to it.
So just concentrate on C, D, E, F, G, H. Yeah?
You already found it for A, so you can just remove B from spanning tree for A, and then...
Yeah, but let's not try to do an incremental algorithm in our head. Just look at it anew and tell me what's the cheapest way to hook all those white vertices together. Yeah?
You want it's 6, right? That's the cost.
I think so, yeah. So we can take C to D, that's 1. D to G is 2. G to H is 3. But now we have to use one of those edges of weight 2. That's 5, and then the one between F and E is 6. So we got 6 plus 4. So we got a bound of 10. So in the interest of time, we'll stop trying to calculate these things. You just have to trust my numbers. If we go from B to C, it turns out the bound is still 10. From C to D, the bound is still 10. Do our bounds do us any good at this point? No, because you've got to have a best so far to compare them against. So we could just not compute them until we actually find a solution. Okay? If you go to E, it turns out now the bound is 11. You go to F, 11. You go to G, 11. You go to H, that's actually a solution, and it's 11. So now we have a benchmark.
We have to get back to A.
Hmm?
We have to get back to A, right?
Yeah.
11 includes the last.
Well, the 11 includes getting to A. All right. So now, let's back up to G. Is there another way out of G that we need to explore? It has to go, we have to find an edge out of G that goes to a white vertex. No. A way to explore out of F? No. Now in your program, there's always going to be other ways out, because there's so many edges. There's not another way edge out there, but there is another way to explore out of D. We could go to G. So let's go to G, and that bound turns out to be infinity if you do it, because it's just going to turn out there's not a spanning tree that connects F, H, and E together. So that infinity is bigger than the 11 that we know. So we don't keep trying to go out of G, we back up. Okay, we go from C to H now. And it turns out, if you do the math, there's a bound of 14 at this point. That's worse than the 11. So we don't have to keep looking out of H. We prune it immediately. So you see how this wins.
Wait, sorry, are you comparing the 14 to the end of the other spanning tree?
This
or
is a lower, if we continue in this way, we can't do every 14. We already know there's a way to solve it in 11. So don't do it. Give up on that. Try a different way. Oops. So back to there, we try E. It has a 10. So we try D. That turns out to be a 15, so heck with that. Try F. That's a 10. That's a 14. Bag it, and so on. So you end up pruning a lot of stuff out the bottom. So the question comes down to, what's an effective way to do the pruning? Okay? So the way I suggest you start this problem is just write a brute force traveling salesman problem solution. It's going to essentially, as efficiently as you can, try all the possibilities until you find the shortest path. Then it's trying to add strategies, then add branch and bound. So let's in a couple minutes here, let's talk about some ways, some easy ways to put a bound on a partial path. It's always going to be the cost of the path you have so far, plus some more stuff. What could you do? Yeah?
In terms of finding a Hamiltonian cycle, because you have like a set of vertices that you've already visited, so you have the weight of your path so far, plus the number of vertices that you need to visit.
Okay.
There's going to be a number.
All right, so all the edges are positive. So you know that, and they're integers, so you know that if you've got 6 vertices left to visit, the cost is going to be at least 6, right? So that's one thing you can do. Just the cost of the path so far, plus the number of vertices you have to come. Can you improve on that? Yeah?
In the traveling salesman problem, are all the edges the same way, or are they?
No, they're all different weights.
That's awesome.
So what would be better than just saying every edge will be at least 1? All the missing edges will be at least 1. Yeah?
Can we get an average of the edges?
Well, don't we go to averages? We got to have lower bounds. Yeah?
You can look at the actual weights out of that vertex because they're readily accessible.
Okay. So you could say, okay, 6 vertices yet to visit, or 6 vertices to find edges out of. You could say, okay, let's figure out what's the lightest edge out of each of these vertices. Okay? That would be a better bound than saying 1. I mean, a better bound would be just figure out you can pre-compute the weight of edges in the graph, and you could just take the 6 lightest remaining edges. It's not hard to think of ways to put bounds on the path to come. The trick is coming up with a technique to do it that's fast, and which is effective. It's a trade-off. Fast and effective. And your basic search code that's exhaustively searching needs to be efficient. So you got to think about efficiency. Yeah?
Should we assume that there is a solution for test cases?
Oh, there's definitely going to, yes, you can assume there's a solution because the graphs are complete. There'll always be a cycle, so there'll always be a lightest cycle. Okay, one more, then we'll stop and revisit this next time. Yeah?
The question on caddis, do we have multiple threads on caddis, or is caddis a single?
It still counts CPU time.
It'll count the CPU time.
All right. So think about this some, and we'll revisit it next time.